Welcome back, everybody, to another digital SAT math lesson with Enriched Scholars. Today, we're going to be talking about two variable data models and scatter plots. So, what's a scatter plot? A scatter plot is when you essentially plot all your data. So, say if you have a data set of maybe 100 people who have different average income, and maybe you're trying to figure out their health quality index. So, maybe it's some sort of a health index, and you're trying to see if people with higher average income tend to receive better health care. And maybe you have a bunch of data, and usually there's some kind of a pattern. For example, here it seems like the more money you're making, the better health care you're getting. Your health on average seems to be better. And the way we can kind of model that pattern is by drawing a line of best fit through the data. And when we draw this line of best fit, what it helps us do is it helps us interpolate. And I'll explain that very quickly. What interpolation means is when you try to make a prediction based on the data, and that prediction you're making, it's not necessarily based on an individual data point. So maybe this person right here, or say this person right here, maybe they're making $300,000 per year. But as you can see, it's a bit of an outlier. And secondly, our actual line, the line of best fit, which is taking all these points into account and trying to predict the line that's the closest to resembling or representing the pattern that's being demonstrated by all this data, that line actually reports a higher average health index for people making $300,000. So in that case, what we're doing is we're taking a value within this range. So that's our range here. That's the range of average income represented in the sample size. And we're trying to predict a value for the health index for an average income within that range based on all the data that we have received, the sample we have collected. So that's interpolation. Extrapolation is risky. So that is if now you try to extrapolate this, extrapolate how much someone with $100 billion would score on the health index. Why is that problematic? Because if you just follow this pattern, and here maybe our income range, our actual sample's income range is something like $50,000 to $400,000, then if you just follow this pattern, then for $100 billion, the health index is going to be like ridiculously high. And it's probably going to predict that this person's going to live for 1,000 years, which doesn't make any sense. So that's why we don't want to extrapolate. We want to make predictions within the range. The y-intercept, you all know, it predicts the y when x is equal to 0. That's the definition of y-intercept. So it's simply just another prediction, but for x is equal to 0. And slope is, by the definition of slope, it's predicted change in y, or the variable that we're plotting on the y-axis, per 1 unit increase in the variable that we're plotting on the x-axis. Now, I want to talk a little bit about a correlation here, because when we're talking about patterns, sometimes you can have a strong pattern, sometimes you can have a weak pattern. So you might have two different sample sizes, and maybe for one of them, it looks something like this. For the other one, it looks something like this. But maybe they have the exact same line of best fit. Okay? Maybe it's something like y is equal to 1.5x plus 0.02. So they both have the exact same line of best fit. But now you need a way of kind of suggesting the person that's reading your statistical results that actually one of these has a much stronger predictive power than the other one. Because this one, we can see the pattern, like all the data is very much condensed around this line of best fit, whereas here we have far more anomalies or far more data that's deviating more from our line of best fit. So this one definitely, the one on the left, definitely has a stronger predictive power. And the way we represent that is with this quantity called a correlation coefficient. And there's different kinds of values you can have for this correlation coefficient. If it's 0 to 0.5, it's weak. If it's 0.5 to 0.8, it's moderate. It's 0.8 to 1, it's strong. But also you want to remember that correlation isn't the same as causation. So just because the data seems to suggest that people with higher income might tend to have better healthcare access, that doesn't mean that is the reason they have better healthcare access. So now in this specific example, maybe it's not the best real world example to use for this concept, but essentially sometimes you have correlations, right? Sometimes you may have something like people who are taking someone scores in like English language tests and someone scores in math tests, and you're just like plotting them. So you're doing math exam scores and you're doing English exam scores, and you see this pattern, you see a strong correlation, but that doesn't mean you can say that these people do better in the math exams because they do well on the English exams. Because it might just be a different factor that's causing both of them. It might just be because they're more hardworking students. They might be more brilliant students. So just because there's a correlation between two variables doesn't mean one variable is necessarily causing the other variable, or one event is causing the other event, rather. Also, linear versus exponential. Sometimes you might have a linear pattern. Other times you might have an exponential pattern. So an exponential pattern is where you have a constant ratio between y values, whereas in a linear pattern you have a constant difference between y values. And the residual is essentially your actual versus predicted. So whatever your curve residual plot is, that's essentially telling you that if your residual plot is actually a curved plot, then that means the linear model is wrong. So by that what I mean is, if you actually have an exponential pattern, so it'll probably look something like this. But now if you try drawing like a linear line of best fit, instead of doing an exponential curve of best fit, which is something that's definitely not tested on the SAT, but if you try to fit a line through it, then what happens is if you start taking these residuals, like how much these are deviating, then you'll see the further you go along the x-axis, the more they start deviating on average. So the plot of residuals would be an exponential fit, would be an exponential curve, and therefore it'll tell you that your linear model is wrong. We can do a quick practice question here. So say a scatter plot with 6 data points in a linear pattern is trending up. Line of best fit passes through approximately 0.02 and 4.2. What's the closest slope of the line of best fit? So here we know approximately it's passing through those points. So it's really just asking you to calculate the slope based on these points, and we know the definition of slope. It's y2 minus y1 over x2 minus x1. So m would be 2 minus 0.2 over 4 minus L. So that gives us 1.98 over 4, or 0.44. So it's actually not 0.44 rather. It's 0.495. But again, you find this slope, and then it's saying what's the closest to the slope of the line of best fit. So this is our slope of the line of best fit, and then the closest value here is 0.44. So the golden rule is just remember slope is change in y per unit change in x, and correlation doesn't imply causation, and if a residual plot shows a curve, that means the linear model is not appropriate. As always, keep practicing, keep improving, and I'll see you in the next video.